Hello everyone, and welcome to the third lecture of Digital Elevation Models and Applications course. And we will continue on this topic, major one, that is the various techniques to generate digital elevation model. So this is part 2. In part 1 we have discussed how from point data we can generate, or from topographic maps we can generate digital elevation models by employing interpolation techniques. But here we will see some other techniques which can be used. So like digital elevation models, as you know, that can be generated using the interpolation techniques which we have already covered. Digital elevation models can also be generated using remote sensing techniques like stereo pairs data, maybe from spot. The technology started with first spot using the photogrammetric techniques, and Cartosat data, which is our own Indian satellite data, and various satellites are providing stereo data. Employing those stereo data, we can use these digital elevation models. SAR has also created a global digital elevation model using the same photogrammetric technique and of course the remote sensing data. Another way of creating digital elevation model by employing the SAR interferometry or in-SAR technology, which is again a remote sensing based technology. And again here we have to use the data pairs, two data sets of the same area, and the data set can come either from NV set, and of course NV set is no more available, but older data is available. But for latest data, the Sentinel data, which is again free of cost, is available on net, and softwares are also available to process the data, which are also in public domain. So just employing this technique, which is in SAR or SAR interferometry, we can also generate digital elevation models. And digital elevation models can also be generated using the Lidar data. Again, this is also a remote sensing method. So we will see some examples how digital elevation models can be generated using Lidar data, especially the DSM, digital surface models. One more technique which developed a few years back by me, that is the thermal infrared data of a hilly terrain, can also be developed using remote sensing method, but at a relatively coarser resolution. So we will see that example as well. So let's go for first, that is the optical remote sensing data images which can be acquired by the satellites as conventionally used in generating DMs which imply the photogrammetric technique. And for example, QuickBird, Iconos, and 2.5 and Pleiades 1B, 1A, 1B constellation, 1 meter resolution, Bird View, GeoView, Japanese, this is ALOS, 2.5, Indian, our Indian Cartosat 2.5. These are the resolutions, and stereo data available. For many data sets it is free, so you can you can develop a digital elevation model even up to 1 meter resolution. In case of spot, which really this technology was first tested with the spot satellite data, and what it was doing, that if you acquire the data of the same area with different angles, minimum 2 angles are required, then you can employ the photogrammetric technique. That means the stereo images will be used, and then using these stereo pair, one can generate digital elevation model. So this is one of the examples. The problem with this kind of data acquisition, like in case of spot, the example is given here, that the same area is being covered 5 days before, say day 0. So 5 days before it was possible to cover with a angle through a steering of a mirror of the sensor. So 5 days before the same area is being scanned, on day 0 it is being scanned. Again 5 days after day 0, it is being, same area is scanned, and after 10 days, same area is. So now we are having two data sets. We may create a stereo pair, and then employing photogrammetric techniques, we can develop a digital elevation model. The problem here was that, say, if you are working in an area where clouds are a big problem, so suppose on day 0 you had a completely cloud free scene, but on day 5, that is plus day 5, you are having cloud cover, and therefore there were problem about getting the data pairs or the image pairs for a stereo generation. Those both or all the should be completely cloud free, otherwise there will be a problem, because here we are using the optical images which is not possible with these images to penetrate through clouds. So that was one of the limitations. So this limitation was sorted out later on in some other satellites, but especially in Cartosat. So that example we will also see. So here the parallax is to be developed using stereo pair data, and this, as mentioned earlier, it was first started with the launching of SPOT, and using such data pairs. Here one example of Mount Pinatubo of that image was acquired. A data pair is required of two different dates, 6th January and then 4th February. Luckily both were cloud free, and then a digital elevation model of the same area was generated. So by this, now here the resolution will depend on the resolution of optical images. If optical images are having resolution, say 10 meter, like in this case of SPOT, panchromatic, then your digital elevation model will also have a 10 meter resolution. So it is a directly depending on the resolution of your original images. But later on technology improved, and as given example now that it is possible even to create a digital elevation model at 1 meter resolution employing same stereo pair based photogrammetric technique. This is the 3D perspective view of the Mount Pinatubo, again generated with the SPOT images, SPOT data pair, and the one image has been draped over that data set. So we can see the advantages of that. First the images were used to generate a digital elevation model, and then one of the images was used which was used to drape over digital elevation model, and then you develop a 3D perspective. So this can be done with any optical images. Now, as mentioned in the problem of clouds which was there with the SPOT or similar kind of satellites was resolved in Cartosat. Of course, the resolution improved to even 2.5 meter resolution instead of 10 meter resolutions, and simultaneously with two different angles the images were acquired, and this was a very simple solution was found, that the satellite used to look in obliquely forward and backward as well. So it was acquiring data of when it is flying over an area, then it is looking through a camera the backward as well as a forward scene. So this is what you see, that true stereo capacity simultaneously two different angles of the same area were covered, two cameras were there together, one is called pan fore and another one is pan aft, and they had a tilt angle of plus 26 degree that was looking forward and minus 5 tilt along the track. So this was the backward, and then this ratio of baseline over height, H ratio, which was 6.62. Of course, swath and other things were different, but a spatial resolution is important to note. Instead of like in a SPOT, in case of a SPOT, it was 10 meter, we could achieve 2.5 meter. And the biggest problem of the clouds or changes meteorological condition changes were not there, because when the four image or the one image is being acquired simultaneously, the other image is also acquired. So it resolved two problems. One is the cloud problem, another one is a spatial resolution. So much improved spatial resolution data is available. I want to add one more information here, that for a large part of India, the NRSA, which is part of ISRO organization, has developed digital elevation models which are available free of cost for Indian territory, some parts of Indian territory, and slowly it is being updated or appended. So more areas are being covered using this Cartosat DM, and this can be downloaded through a Google-like product which is called Bhuvan. So on Bhuvan, Cartosat based digital elevation models at relatively high resolutions, may not be 2.5, around 5 meter resolution, can be downloaded for many parts of India. So that can be very useful, because the other global digital elevation models which are available today, none of them are close to 5 meter. So in that way, it is quite good. And these are the examples. This camera 4A, pan 4A and fan after is the example is here, that they are covering the same area at the same time. And this is how the images will look. When you see two images which have been acquired at the same time, and but you don't see individually much difference, but when you see through either these use as a stereo products and then use the photogrammetric technique, then definitely a digital elevation model can be prepared using this, and this is how this has been employed. Further examples, the draping and other things, that this is the one example of Cartosat DM of a part of Ankara, Turkey. And here what we are seeing, the first digital elevation model was generated, and over that the image has been, this image has been draped, and this is what we see in really good 3D at quite high resolution of at 2.5 meter. Now, because as I have mentioned that there are many, nowadays I can say many, more than 2-3 digital elevation models are available, and the complete list we will be seeing in subsequent lectures. But just to compare two DMs of part of Arunachal Pradesh and how they look. So exactly the same area has been displayed here. One is SRTM DM of the same resolution, spatial resolution. In both the cases it is 30 meter. And we hardly see any difference. But the important thing here to note that the technologies which have been employed to generate these two DMs are completely different. Because in case of SRTM DM, the INSAR technology has been employed, which we are going to discuss very soon. And in case of Aster DM, stereo pair, which the technique which we have just discussed briefly, has been employed. But the product which has been generated are quite close or quite looks very similar, at least at visual level. So, but if we go further, then we have found that SRTM is not good for hilly terrain because it implies the SAR interferometry technique, and radar remote sensing is having some problems in a hilly terrain, especially like Himalayan, which is highly rugged terrain. But for plain areas, SRTM is good. In comparison to SRTM, Aster DM is good for hilly terrains, but it is not that good as for plain areas. So if somebody is working for plain areas, then one should employ the SRTM. If Cartosat DM for that area at higher spatial resolution is not available, then SRTM can be employed. Or if somebody is working for hilly terrain, then it would be better to employ S-TM. This I am telling based on certain comparative studies which we have employed, and using also confirming with the point data which we are available for certain areas. So by doing this comparison exercise, we reach to this conclusion that SRTM is good for plain areas, S-TM is good for hilly regions. Another technique which in SAR or SAR interferometry technique, which is one of the very powerful technique now has been established, and not only for generating digital elevation models, because the advantage with the radar remote sensing is that even in a cloudy conditions, it can acquire the data. Second is that it is not only daytime, because you don't need the solar energy to acquire the data. The energy which is required to acquire the data is sent by the satellite itself. So therefore the data can be acquired in any weather condition one, and also day and night, any time of the day. So that's the one of the biggest advantages with the radar data. And when we go for interferometry, that means we require a pair of the same area covered with again two different angles. So this two passes, and the examples are first started with the like ERS, and later on radar set, Terra, SAR X, NVSat SR, that was the name of the sensor on NVSat satellite, then Sentinel, which is currently operational, and this data is available. So that when we can get the two images or a pair, then it can be used to generate elevation map, which is maybe at very high resolution, around 10 meter or so. And the advantage is that nowadays this data is available free, and products are coming. These are based on global product, global DMs are coming, which have been generated using these data sets, especially like Sentinel or others. So the first example of SRTM INSAR or INSAR technology based was example I have already taken, that this was a mission. It was not really a satellite, but it was a mission, and roughly in 10 days time, the 80% of the globe was covered, and the technology which was employed here through a, because in radar interferometry or SAR interferometry, the baseline is a big issue. So there is a long shaft was used to acquire the data from two different angles, and this mission lasted about 10 days, and 80% of the globe was covered with two different angles data, as you can see, theta 1, theta 2, and then this was processed through photogrammetric techniques, and digital elevation model at different resolution, 90 meter, 30 meter, were generated for almost all parts of the globe except for polar regions. One example from radar set, that DM can also be generated employing same SAR interferometry technique. So radar set had the capability of steerable beam with the 7 steerable beams, and it used to acquire data in that manner. Stereo pair were made finally, and then you process the data, and ultimately finally you get the digital elevation model at a resolution, the same resolution as the data was being acquired. The example here, again the stereo pair of this data, and this is the digital elevation model of Brunei generated from radar set employing SAR interferometry technique. Another example here, which is one of the other satellite is coming, which is ALOS pulsar. So what here we are seeing in the top left image is a true color Landsat image just for visualization, and for the same area we are now seeing this ALOS pulsar image, which is having this resolution using this ALOS pulsar data pair, a digital elevation model on the bottom left, is shown here, which was generated at 12.5 meter resolution of a region of Kutch region of Gujarat, India, and a steady relief model generated from this Allos pulsar DM is also shown here. So you can compare that this is the optical image from Landsat, this is power image or radar image from Allos pulsar, and the data pair of Allos pulsar has been used to generate a digital elevation model at 12.5 meter, and then finally hillside is generated. You can use this data for various purposes, but just one product which is very common, looks nice, has also been shown in this example. So various options are available to generate digital elevation models even using SAR interferometry and radar technology. One more comparison is here that this is SRTM at 90 meter and this is SRTM at 30 meter. Again Aster DM at 30 meter, which you can compare 30 meter, but still SRTM is also quite comparable, and then Allos pulsar 12.5 meter. So when we compare this 90 meter to 12.5 meter, definitely there is a difference, and finer details in this 12.5 meter can be seen, as those may not be visible at a relatively low resolution image. And this is again the same part, which is the Kutch region of Gujarat. So if options are available, that if you are having for the same area multiple digital elevation models are available, one can do first a comparative study and then assess which one is the most accurate by employing some point observations or getting data from differential GPS or already collected data by some other organization. Then you can use that data, input data, point data, and compare against the data which has been generated, or elevation models which has been generated employing different techniques, and then one can use further for various analysis. Now another example is from Lidar, Lidar is a light detection and ranging technique. I am not going to in detail of how Lidar really works, but Lidar generates the DSM, the digital surface model. So again Lidar is a remote sensing technique, and here instead of working in microwave region, it sends the light, visible light in form of pulse laser to measure the ranges or distance to the earth. Now these lights pulses combined with other data recorded by airborne system which generate precise three-dimensional information, and that means this data can be used also to generate a digital elevation model, and this is what we do. So this is the example here. What we see, this is the real photograph of that area, and but what you are seeing that this is from the top and this is the profile view. So both things are here can be seen, and this is how a Lidar image will look like. So here Lidar data is often collected by aircrafts, and of course the satellite Lidar based on some satellites is still not a very ready one, but airborne Lidar is very common. Also Lidar provides a opportunity to generate very high quality digital elevation models at a very high resolution, because it's a ground based, so we can generate much more higher elevation models. As I have said that this generates the DSM, so first return surface, which includes tree canopy and buildings. It is often referred as a digital surface model. So in the example which we have seen here with the Lidar, it is showing the DSM, not really a digital elevation model, but later the ground or bare earth contains only topography, and which we call as a digital elevation model. So when we compare with the Lidar DM with the same resolution corresponding the same area, with say USGS 10 meter resolution, because Lidar has generated a surface model rather than elevation model, and therefore you see lot of differences. But there are techniques are available by which you can remove this canopy and buildings from the surface, and a bare digital elevation model can also be generated. So all kinds of options nowadays are available to generate digital elevation model. One more example we see here, which is national elevation data of US at 10 meter resolution versus Lidar of 1.5 meter resolution. So see, is a 1.5 meter resolution. This is bare earth. This is not DSM. This is really a DM with comparing DM of 10 meter resolution. Of course, there is a huge difference between the resolution, spatial resolution, and therefore you are seeing much detailed information which is missing in 10 meter resolution. We know very well that if resolution improves, then the more details will be available for us. So that it depends on basically what is the requirement, project requirement, the work requirement, and depending on that, one should choose the spatial resolution of a digital elevation model. The first choice, of course, is available through the free digital elevation models, but if it is not sufficient for requirement of a project, maybe some construction sites, maybe a dam site, or for landslide studies, for route alignments, any civil engineering problems, or looking for some other things, then digital elevation models at higher resolutions for a small area can also be generated, as we have seen various techniques that either you use the ground survey techniques or use the stereo pair data of very high resolution, say Cartosat 2.5 meter, 4 meter, 5 meter resolution, or maybe some other in SAR technology, and some other technologies can be employed, and therefore digital elevation models almost at desired spatial resolution are now possible to generate. So this brings to the end of this presentation. Thank you very much.